Good evening, everyone. My name's Beth Weigel. I'm the program coordinator for the Juneau Public Libraries, and we're very excited for the presentation tonight with our representative from NASA. This is very exciting for us and our community. Before we get started, I just wanted to give a few shout outs and thank yous to have the folks and the organizations that made it possible for Dr. Edwards to be here tonight. Of course, we worked really well with NASA, and we have to just say so many thank yous to NASA for bringing Dr. Edwards to town tonight. Also, this is part of our ongoing Science on Screen series at the Juneau Public Libraries. The Friends of the Juneau Public Libraries, Goldtown Theater, and the library have been putting together talks that pair a scientist with a film. So this is the last in that series, and you can also watch the film Agora, which is connected to the talk tonight a little bit. He'll tell us how, over at the Goldtown for free at 9 o'clock or on Monday at 7 o'clock. And the Science on Screen is brought to us through a grant through the Coolidge Corner Theater and the Alfred P. Sloan Foundation. So we're also kicking off our NASA at My Library program. We received a grant at the library for NASA at My Library. It's part of the American Library Association programs, and so we're kicking off that program tonight. We'll have lots more programming at the library with fun kits and a lot of programming for kids as well. So that's also want to say thank you to all the folks that helped make that happen. So tonight our speaker is Dr. Thomas Edwards, and he comes to us from the Ames Research Center in California. He's the deputy director there. And he began his career with NASA in 1983. He's been involved with things like computational fluid dynamics, aircraft design, aerothermodynamics, information technology, and aviation operations. He's a graduate of Princeton University with a master's and a doctorate in aeronautics and astronautics from Stanford University. Please welcome Dr. Thomas Edwards. Yes.
Thank you very much, Beth, and thank you, Juneau, for inviting me up here. It really wasn't that hard to get me to come up here. I love Alaska, and I get up here every chance I can, and so it's always a pleasure to come back here and visit. Let me start. We're going to cover a lot of things tonight about what NASA is doing, how it's connected to history, and also how it's connected to Alaska. A lot of technical subjects, and so I invite you to kind of tune in when something in particular strikes your interest, save a question in your head, and I'll try to save enough time at the end so that we can answer some questions. That really is a lot of times the most fun in these things. One thing I can get out of the way right away is sort of where I came from and who I am. Not the central subject of tonight, but as Beth said, I am an admitted space geek. At the age of 10, I owned my first telescope, and I still have it today, and I still use it. So I was staring up at the heavens for a long time, wondering what's out there. I got interested in how airplanes fly, and as I went through school, I kind of got a passion for mathematics, and all of that kind of rolls together into aerospace engineering. And from that, you can go in many different directions. And within NASA, we have lots of aerospace engineers working on many different things, a lot of which you'll hear about tonight. So we're strong proponents of education, particularly in the STEM fields, science, technology, engineering, and mathematics. And we really love to come out and talk to audiences at schools and to the public to spread the word and to try to get other people excited about it, and perhaps some who want to come work for NASA someday. We have really cool internship programs across the whole of NASA where students who are in college can come spend a summer or even a quarter during the school year and work side by side with scientists on real projects. It's a fantastic opportunity, and I can tell you more about that later too. So let me get started though with what I really want to tell you about, which is all about this agency that I have spent 34 years at. And it's been a wonderful 34 years. If I had another 34 to work, I would stay right where I am. It is fantastic work. It's an exciting mission, and it's just been a real joy to support it all the way through. For many years, I was one of the engineers working on flight projects, designing aircraft, looking at new spacecraft and different concepts for space flight. And then over the years, I started managing groups of people, and ultimately I got to where I am now, which is the number 2 guy at Ames Research Center, which is very close to San Francisco. And we do a variety of things at Ames that support the entire breadth of things I'll be telling you about in the space program. So it's kind of like a university, and we work in many different areas. I've moved from aerodynamics to computer science to space flight and everything in between. So let me get started and share some of those things with you. First of all, though, when you think of NASA, most people are doing pretty well if they can think of 1 or 2 things that we do. So you probably know we build really big rockets, and we build and fly them. And we go to Mars, and we hear a lot about that. And then we have these telescopes that peer into the depths of space and show these beautiful images of what's out there. So yes, those are all things that NASA does, but that's really just scratching the surface. And there's a whole lot going on within NASA that it really, we don't get to get the headlines every day. We'd love to tell everybody about everything we're doing every day, but we don't. And so these things make the headlines. There's a lot of other things that we do that are covering a lot of other things. And we kind of made movie posters out of them here to give a little bit more public appeal to describing what we do. And so you can take a quick look at these pictures. I'm going to go through each one of these and tell you how we are impacting everything on this, from looking back at the Earth to peering into the depths of space. So let's go ahead and get started. It starts with the first A in NASA. So anybody know what the first A in NASA is for? Aeronautics. All right. So aeronautics is where NASA began. And we actually began as the National Advisory Committee on Aeronautics in 1917. And for the better part of 40 years, that's what the agency did. In 1958, the Space Act was passed by Congress and signed into law, which formed NASA, the National Aeronautics and Space Administration. So we have a very long heritage in aeronautics, and we still today devote a lot of our attention to improving aeronautics and aviation for the American public. We kind of look at that, the needs in aeronautics in these 3 areas here that we call the global drivers that push the need for new technology in aeronautics. The first one is the global growth and demand for high-speed mobility. And by high speed, we mean flying, because that is the fastest way to get from point A to point B. And without interruption, over the decades that we have been flying, the demand for air transportation has been increasing. In fact, it's been increasing at an increasing rate with the advent of online delivery, buy something and have it delivered overnight, and with the rise in international trade, the demand for travel is increasing. So that means more airplanes, more airports, and more congestion in the airspace. And that's a problem that we're working to solve. The second major driver is affordability, sustainability, and energy use. So right now, aviation represents a fairly small fraction of the overall carbon emissions for the planet. It's around 2 or 3%, so it doesn't sound like much, doesn't sound like we should worry about it, but we do, because it's still a big number, it is growing, and we want aviation to be a very good neighbor to the people who live around airports as well as the entire public. So we take a look at what we can do about the emissions, the fuel efficiency, and even the noise that aircraft make around airports, so that we are better neighbors to the community. And the final one is sort of an intriguing topic we call technology convergence. And this is sort of the magic that can happen when 2 different technologies come together and make something really fantastic. So we can think of, for example, computer power, which computers get faster and faster, cheaper and cheaper, smaller and smaller every year. And along with that, we can look at, for example, GPS, Global Positioning System. With very fast computers, and very accurate navigation, we can now do things to manage the way aircraft fly that we never could have done before. And we're using that to make aviation more efficient, safer, more comfortable, and so forth. So those are the drivers that we're looking at when we say, well, what should we be doing in aeronautics and aviation? And what that ends up in terms of the actual things that our aerospace engineers are doing is working on air traffic management. We actually look at the flows of traffic and develop computer programs that manage flights better than a human who's overwhelmed with more than a dozen or so aircraft to manage at a time. And so we have inserted technology throughout the airspace management system that is helping aircraft get around faster, more efficiently, and avoiding the congestion that we see a lot of times. Ultra efficient commercial vehicles. For years and years and years, when you look up in the air and you see a commercial airplane flying around, what you see is a long skinny tube with two wings coming out of it. That's pretty much the state of the art. Now, there have been a lot of subtle changes that have made those aircraft better, more efficient, and safer, but when you look up, that's pretty much, the view has not changed. That's about to change now, because we are looking at how we get to the next level of fuel efficiency for commercial aircraft. And the only way to do that, we've determined, is to go to a different type of configuration. And there is no one right answer yet. We're looking at several, and we hope in the coming years to actually build some new X-planes that will demonstrate the capabilities of these new aircraft. Some of them might look like a flying wing. Some of them look like the fuselage kind of got squashed, and so it's a little flatter than it used to be, but it's got more volume and more lift. So there are a number of very promising concepts. We're looking forward to flight testing those. We've done lots of evaluations so far. This one here is the one that really puts a twinkle in my eye. We have been working on supersonic flight, well, of course, since the 60s, and Concorde was a great demonstration of how an airplane can fly supersonically. Unfortunately, it was not a commercial success, and the sonic boom was so loud that supersonic flight over land was banned, and it still is today. Commercial aircraft cannot fly supersonically over land, the reason being the public objects. What we have found, and this is something was working on about 20 years ago, through advanced computational tools and advanced design methodologies, we can manage that sonic boom to a point where you hardly know it's there. We've actually figured out a way to mitigate that sonic boom so that it's no different in the noise characteristic as a bus driving down the street. So if you're willing to let that bus drive down the street, we can develop an airplane that can fly 2 times the speed of sound, about 3 times faster than you can fly in a commercial airplane today, and will not disturb the public underneath it. We're very hopeful about this, and in the next year or so, we hope to build and fly the demonstrator that shows this works. We are looking at how to get off of fossil fuels for aviation, so we're looking at hybrid electric propulsion systems and all-electric aircraft. And then the other really exciting one is unmanned aerial systems. That's the official NASA term for it. You probably heard of them as drones. And these are really exciting for a multitude of applications. Everybody wants to fly drones to do taking pictures, to delivering pizza to your doorstep, whatever you want to do with a drone. It's a huge demand growing. The problem is we don't have the rules in place for how to make that safe. And so right now it is very, very restricted. And so what NASA is working on right now is the system that will allow these drones to fly pretty much at will. File and fly is what we call it, so that anyone who wants to operate either commercially or recreationally, there's a set of rules and there's a system in place that makes sure everybody is safe, that the aircraft are separated, everybody knows where everybody else is, and we avoid the kind of problems that we might encounter without it. And so we're moving through that. In fact, I'll tell you in a minute about some work we're doing up here in Alaska that is participating with our experiment in this system. So I mentioned about designing airplanes. I just want to point out there's two major ways that we design airplanes at NASA. One is through experiments on the ground, and those are using wind tunnels. So we have really big wind tunnels. In fact, where I work, we have the biggest wind tunnel in the world. It's so big, you can fit a full-scale 737 into the wind tunnel and run the air past it at 100 miles an hour. We haven't done that because that's not really a practical thing to do, but we like to say we could. We have, but we are able to test really big things in that wind tunnel. We've tested all of the parachutes that are used for the Mars lander systems. We've tested full-scale trucks for their aerodynamics, fighter jets, helicopters, you name it. So we put articles in wind tunnels and blow the air past them very fast, and then we take measurements. And you can see images here that show the kinds of measurements we take. We can look at shock waves when something is flying supersonically. We use lasers to actually measure the velocity of the air and how it changes its direction when it goes around flight vehicles. And we have good old-fashioned force and moment balances that are kind of like spring balances that measure forces also. So lots and lots of wind tunnel testing is still a very heavily used technique. But in the time since I started working, the advent of a discipline called computational fluid dynamics has come around, where we can do the same thing with a computer. You need a really, really big computer, very fast computer, and so we operate the agency's supercomputer that calculates flows that we want to learn about. And when I started long, long ago, the best we could do was a little very simple looking wing and to look at the lift and drag on it. But right here, you're looking at examples of very sophisticated simulations. This is the airflow over what we call our space launch system that's going to ultimately go to Mars someday. We're looking at landing gear noise when an airplane is on approach for landing. We can look at the flow through a jet engine and look at the efficiency and the noise generated and look at design trades. So modeling and simulation has become another major component of how we calculate and design aircraft and spacecraft. Anything that flies through the atmosphere, we're using supercomputers to look at those. So I mentioned air traffic management and the convergence of these technologies that allowed us to very accurately predict where an airplane is at any point in time, and then to aggregate that picture with all the aircraft in the airspace, and then develop a smart scheduler that figures out who goes first, how far apart do we space them, provides all that information to air traffic controllers, and they can line up and land aircraft at significantly higher rates than they used to when all the math was done up in their head. Which is not to take anything away from air traffic controllers. They are extremely good at mental math, and they can do calculations in real time that I can't even imagine doing to figure out how far apart aircraft are and when they need to make turns. But there are now so many aircraft in the air and so many that want to get in the air that it's even more than the humans can handle. So that's where the computers come in, that's where NASA comes in, and we work very closely with the FAA to provide that technology. And I told you about the UAS traffic management, which ultimately may be the way we fly aircraft throughout the airspace. But for right now, we're looking at just kind of what we call Class G airspace, 500 feet and below. And here up in Alaska, we had a project running for a while we called Taiga. And the problem it was trying to address, this came about as a result of discussions that we had with the Alaskan aviation community. There's really a lack of availability of good weather information for general aviation pilots, to the extent the weather changes so fast up here that even if there's a clear weather report when a GA pilot takes off, when they get to the pass that they need to get through to go where they want to go, the weather may have changed. And so what we worked with them on is a system that took advantage of satellite communication, a display system that was used in the cockpit of a general aviation aircraft, and the data sources necessary to provide them the information and the interfaces needed to make intelligent decisions. Should I go for the pass or should I turn around and try another day? And so this has been a really fun and successful project. And in the end, we developed moving map displays that now are available for GA pilots in Alaska. It's been commercialized, so we turned the technology over, and now they can use this in the cockpit to identify where the hazards are and whether it's a good day or not to fly into the mountains where they want to go. So we continue the dialogue, and we're looking for what can we do next. So let's turn now to Earth science. The tagline here says, your planet is changing, we're on it. And what that means is that a big part of NASA's mission is to look right back down at the Earth. There's a lot of good reasons for doing that. And nearly half of our satellites that are in space right now are looking down at the Earth. They're not looking out at the depths of space, they're looking right back down at the Earth. For one thing, we live here. We care about what it's like here, and we want to understand the dynamics of our planet. It's a very complicated system, and there's all kinds of things going on: the atmosphere, the oceans, all of the energy that comes and goes, and then human activity. So we have a lot of assets that we're using to understand what's going on right here on Earth for the benefit of us who live here, but also it's the only planet we know that has life on it. We hope we find another one someday, but for now, the better we understand this planet, the better we know what to look for. So there are lots and lots of satellites up there that are looking back down at the Earth for different reasons, and you can see here some examples. We're looking at water, particularly where I live in California. We're just coming out of a 6-year drought, and so we've been looking at soil moisture to understand where's the water table, where is the soil wet, where is it dry, what are the implications on agriculture, on land use management, the risk of forest fire, and so forth. So watching the water is an important one. Understanding climate change. Where is the climate changing? The effects are not uniform everywhere. So in some places, changes are more rapid, in others they're fairly benign. We need to understand why that's happening. And so here you can see we're modeling the currents of atmospheric currents around the world to see how energy gets moved from one place to another and what implications that has on the weather and climate in various parts of the world. We go out and fly through hurricanes, even piloted aircraft. We're starting to send drones out there too. It's a little safer for the pilots. And for the pilots tell us it's a pretty bumpy ride, but we need to understand the energetics of hurricanes and how to better predict their trajectories and their intensity and so forth. And so we'll go out there with radar and lasers and look through the clouds in the hurricanes to understand where they're going and how they're evolving. And then we spend a lot of time looking at ice. We spend a lot of time up at the Arctic and also a lot of time down in the Antarctic looking at the ice to see what's going on with it. We care a lot about whether we're looking at one-year-old ice or multi-year ice, how much coverage of land and sea there is with ice. That is a very important factor in how much energy gets reflected out into space. And also, how deep is the ice? Are the ice sheets thinning, and if so, at what rate, and what implications does that have on things like sea level rise and the overall energy balance of the planet? So all of these things produce volumes and volumes of data, and that's our product. We provide the data and the knowledge about what's going on. We don't make policy. That's one thing that NASA does not get into, and so we're the ones to provide the information to those who need to make the decisions about what to do about it. So up here in Alaska, for quite a few years, there's a project called ABOVE. It's a clever creation of an acronym that stands for Arctic Boreal Vulnerability Experiment, and we'll be up here this summer with drones looking down at the tundra. And some of the tundra is starting to thaw, and we're very interested in how much carbon dioxide and methane comes off of the tundra when that happens, because that's a change. The permafrost used to hold everything locked in. Now as it thaws, it's going to be releasing organics into the atmosphere, and we need to understand how much and what the implications of that are. And so we'll be up here again. Unfortunately, I don't get to come on that trip. So, International Space Station, another big activity of ours. And this is Scott Kelly, who recently returned from a year in space while his twin brother tried to pretend that he was doing the same things his brother was. And we compared what they experienced and what was going on with them to understand a lot about how humans can live in space. So there's a whole bunch of things we're doing on the space station. We finally finished building it, and now we want to use it. The only way we can really use it well is to have a good transportation system up there. We used to fly the space shuttle, remember? But we knew that if we ever wanted to get to Mars, we needed something else. The space shuttle was never designed and could not be fixed to go far into deep space to the moon or Mars. So we needed a new space launch system. Unfortunately, we can't operate one and build another one at the same time. So we had to retire the shuttle so that we could start building the next one. And in the meantime, we still need to get up and down to the space station. And for the past several years, that's been solely through the Russians, who have a launch capability that we use routinely. But at the same time, we were spurring the creation of a new commercial industry for space launch. And we're very pleased that there are now several commercial entities that are providing launch services for us. And in about another year or two, they're going to be certified to launch astronauts. So once again, we will have an American capability to launch astronauts into space. We're looking forward to that. But in the meantime, we've got Boeing, SpaceX, we've got Orbital. We've also, coming up very soon, we've got Blue Origin and Sierra Nevada, two other companies that are almost ready to start operating rockets launching payloads into space. So there's just a tremendous amount of activity getting a commercial industry that can support our needs. And that's fantastic, because now we can buy the service instead of operating the service. And that allows us to focus on what we really want to do, which is get out into deep space. In the meantime, though, we're doing a tremendous amount of research on the space station, on board the space station itself. The astronauts that are on the space station, typically 3 Americans and 3 Russians, or 3 Russians and America gets to, sometimes we bring international partners along with us. So crew of 6, they are busy. Their time is managed down to the minute. If you thought homework was bad, that is nothing. These guys, they have armies of people on the ground who are managing every minute that they are going to be moving some. You do an experiment here. As soon as you're done with that, you turn and you're doing another experiment. You're setting up something. You're fixing something. Occasionally you have to step outside and fix something else. So they are very, very busy doing all kinds of experiments for us. And there's a few pictures here that describe the kind of things we're doing. But our principal interest is understanding what it takes to support life in space. And for the astronauts on the space station, there are 2 major aspects of living in space that they have to endure. One is, we call it microgravity. It's not really 0G, but it's very, very, very small. So small, for all intents and purposes, they feel weightless. That has physiological effects. And a lot of them you've heard about over the years. Bone depletion, muscle atrophy, but we're starting to see other effects that we need to mitigate and understand better too. There's the intraocular pressure in your eyes, kind of like glaucoma, is something that some of the astronauts experience, and we need to figure out how to counteract that. There are some concerns about long-term immune system functioning in space. We don't fully understand whether this is something that is going to happen every time, and what do we do about it. The other aspect of the space environment, of course, is radiation. And the space station itself is very well shielded, but nevertheless, there is more radiation in space than we're very well protected here on Earth. And so we need to understand how to protect astronauts' human lives from the radiation of space, and ideally with systems that aren't as heavy as lead shielding or something, just creating a huge barrier. So we're looking at single-celled organisms, trying to propagate them and see how they do in space. We've got animal experiments going on in space. This astronaut here is holding a little container of fruit flies. Very interesting to watch fruit flies try to fly in 0G. It's not mean, but it's funny. We also developed these, what originally were called personal satellite assistants. If you remember Star Wars, then Luke was learning how to use a lightsaber against a little sphere that was trying to get him. I think we were probably inspired by that, but we've developed an astronaut assistant that basically is right there next to them. It's got its own little propulsion system with little CO2 jets that can move it around. And it can take care of routine tasks like data processing, taking pictures, and other things that then frees the astronaut up to do other types of things that are more complicated. Let's see, and then we're also looking just at building tools in space. So that's a wrench there. It's hard to see, but that wrench is no ordinary wrench. That's the first tool that was built with a 3D printer in space. And so we emailed up the design for that, and they built it in space. And this is going to really revolutionize how we don't have to take every spare part with us if we can make the 3D printers create the parts from raw material that we bring along with us. So that will be a tremendous help. So these are just some of the things we're thinking about. How do we support human life in space? In addition to that, on the space station, there are a lot of things we learn that help us down here on Earth. We can produce crystals, proteins, pharmaceuticals in space that are far more pure than what we can do in the gravity environment on the ground. And so it may be that there are certain manufacturing processes in the future that will be conducted in space and then brought back to Earth, supported, of course, by a commercial space industry. So that could be really cool. Okay, so aside from that, there's lots of other bits and pieces that we need technologically to get where we want to go. And so I can just tell you that we do lots of testing on the ground, but we need new rocket propulsions. We need more rocket scientists out there. So if you want to be a rocket scientist, we would love to have you. We need to get beyond the chemical propulsion that we use today. We use oxygen and any variety of fuel, kerosene, hydrogen, hydrazine, all kinds of chemicals that produce lots of thrust, but they're very heavy. A lot of times they're very dangerous. And they also don't produce as much thrust as we'd like them to. They're not as efficient as we would like them to be. And so we're looking at all kinds of new concepts for space propulsion. Electric ion propulsion, solar electric, nuclear. We're looking at anything that might become the next thing that gets us around the solar system more efficiently, and someday to go even beyond the solar system. So we're paying a lot of attention to that. Living in space, beyond just the human physiology parts of it, we have to figure out how to feed ourselves in space, because we can't just pack astronaut space bars and Tang and live on that for the whole duration of a multi-year. So yes, we are growing food on the space station. And so we're learning how much we can produce and how to do it, and how to make it as productive as possible. And then how to utilize the elements that we may encounter if we go to the moon or we go to Mars. There are resources there that we can use. We can pick up and live off the land a little bit. So there's been quite a bit of press recently. Maybe you've seen about how we figured out maybe how to grow potatoes on Mars. Does that sound like a familiar idea? Sometimes life imitates art, and it turns out the potatoes are a very good candidate because they're very hardy. They don't need lots of high nutrient-rich soil, and Matt Damon loved them. And so, you know, how could you not like that? We also develop instruments. I'll say a little bit more about the instruments in a minute, because the application of those instruments is much more interesting when I get to that point. Robotics and computing, again, everything we do now requires huge computing power, and we'd like it to be small and light and low energy use and so forth. And so we're looking at new ways of using computers and new ways of computing, like quantum computing, maybe you've heard of, that could just revolutionize the power of computers and the size and the weight of them. And so we have this huge portfolio of technology that's all trying to get us to be like that guy. And so really, we have Mars in our mind. We've kind of had that destination as our goal for a long time. There are different ways to get there. And so we may not be going directly from Earth to Mars. And that's something that we just continue to study. What's the best way to do that? Maybe going to the moon first, kind of set up a staging area, create some resources that you need, and then go from there. Maybe it's better to go somewhere out into deep space and kind of have a depot out there that we could build up and live long term, and then have kind of excursions that go out to Mars and wherever else we might want to go. So these things are called architectures, and we study those continually to look at the technology trades, what's going to work best. And right now, the way we think of it, there are really three major regimes that we look at for getting to Mars. The first one I've talked about quite a bit already is called Earth reliant. That means space station, low Earth orbit, you can get home in hours if you need to, if anything goes wrong. Bring everything you need with you and take your trash back home with you. So we've got that one pretty well in hand, and it's a great place to conduct our research. The middle one, which you could think of as being on the way to the moon, in that vicinity, we call that the proving ground, because when you're out there, you're a little bit farther from home. Something goes wrong, you can't get back right away. It's going to take a few days, and you're probably going to need to be able to take care of yourself for a little while during that time. And you're also out in that fully exposed environment of space, all the radiation and zero gravity and so forth. And so you really got to have that part figured out. Finally, you get so far away, we're what we call Earth independent. We have provided, in that case, everything you need to take care of yourself. The food, the energy, the medical capabilities, etc. All of that, we've got it all figured out, and we can continue on indefinitely in that environment. That's ultimately where we're headed. And we need to develop those technologies. There's a lot of stuff that needs to get done before we can say we are truly independent. But that's kind of what guides us into the future. And last but not least, this one says NASA, we're out there. And this is the part where you see the amazing photographs of the universe in all different stages and distances and formations. This is a grand quest to understand the universe and kind of to understand our place in it too. So you can see some familiar names here. Hubble Space Telescope, some of the most beautiful pictures of space I've ever seen from that. That's a space-based telescope. And we're about to launch the next great telescope, and that's this one here called James Webb. It's going to be even bigger than Hubble, and it's going to image a broader spectrum, if you will, from light that you can't see all the way up to X-rays. So it's a much broader spectrum, and we'll be able to look much farther into the universe, which essentially means farther back in time, to understand the origins of the universe. So that one is going to launch in a couple of years. It's going to be tremendously exciting to have that one go into operation. We have a telescope that's inside a 747, and that one flies out of California, and it actually flies around at night and makes observations of the sky, and then it comes home. And the cool thing about that is that we can repair it and upgrade it every night, every day, so that when it flies at night, it's got the latest and greatest. When you launch a space telescope, you know, cross your fingers, and that it's pretty much where it's going to be. And so we can do some things with the telescope that's on an airplane that we can't do otherwise. But it also has limitations in its capabilities. We're looking at places that we're starting to get curious about. Is there life there? And if so, how would we find it? I'm going to say a little bit more about this one in the middle also in a minute. So let me just tell you about Kepler. And this does kind of bring us back to the movie that I hope you'll all go see. The question is, here we are. This is a fairly unique planet, we think. How many of them are there out there elsewhere? Because there's really only one in our solar system. Mars, sort of a small sister to Earth, and Venus isn't habitable by our understanding. So where else will we find an Earth? So this launched the mission we call Kepler, which is a telescope that is staring into a distant piece of space that has lots and lots of stars in it. And what it was doing is this technique we call transit photometry. And if you can see, we're looking at a distant star here, and there's a little planet that's passing in front of that star. And when that happens, we measure the brightness. And when the planet passes in front of that star, there's a little dip in the light of that star. And when it goes back around the backside, the light comes back up. So that's what Kepler is looking at, a little piece of space, trying to look for variations in the brightness of stars. Now, if you see a little twinkle like that, there are lots of reasons it could have occurred. There could have been some random piece of rock go in front, or some aberration in space that caused that to happen. So you wait, and you keep looking, and then you see that little twinkle again. And after you see that second one, you know how long it took between those two little twinkles. So then you wait. And if it happens again after the same amount of time, you say, aha, I think I have a planet, because I'm getting a periodic variation in that light. Now, just for reference, that dip in the light is minute. We've got this 1,000,000 pixel camera staring tens of light years into space. And it's effectively the same as if we're here in Juneau and we could see Los Angeles and somebody turns off a 60-watt light bulb. You would see that dip in light. That's kind of what Kepler is doing. So when we launched Kepler about 8 years ago, we held our breath because we didn't know if we were going to find any planets. And it takes a long time, right? This planet, let's say it's an Earth-like planet, it would take 3 years before you could even say, I think I have a planet. And then you've got to wait, and you've got to do independent observations and all kinds of stuff to say, yes, that is a planet. So we waited very anxiously, and we found one. And that was awesome, because that meant, yes, the method works, and there's another planet out there. So then we said, well, how many of them are there? And so we waited, and we looked more and more. Long story short, to date, 8 years into operations, in this little piece of sky that we're looking at, which is about the size of a quarter held at arm's length, that's about the size of sky we're looking at, we found 4,700 candidate planets. They have to be independently confirmed. And independently confirmed, about half that number so far, but there's astronomers all over the world analyzing our data, helping us confirm these. And then the ones we get really interested in are the Earth-like ones, the ones that are in the right distance from their star, that they could have liquid water, that they've got rocky surface, and they're about the size of Earth, so that the gravity would be about right also. And of those, 21 so far, which is really amazing, because when you extrapolate that little piece of sky we're looking at to our entire galaxy, and then to the 300 billion or so other galaxies, I think Star Trek got it right. Just about every star they went to, right, there was a planet that they found that they could go land on. And so it turns out that planets are the norm. It is actually very common to see planets around stars. We didn't know that until Kepler figured this out. And that many times those are Earth-like stars. So here's some data on what kind of stars. So some of them are big and uninteresting, at least in terms of life like we know it. Jupiter size and bigger, and gas giants, and too hot or too close to their star. But we found these Earth-like planets around a variety of stars. So stars like ours, smaller stars, you have to be a little closer, because it's like the campfire. As it goes down, you got to get a little closer to stay warm. So we found these Earth-like planets. So now we say, okay, that's cool. We got planets that might support life. Oh, there's even one that's, or many of them actually, like Tatooine. Binary stars. There are lots of these. So that was, we found, the first time we found them though, I told my daughter, who is a Star Wars junkie, and she was thrilled. We found Tatooine. So we find these planets. Now we want to find out if there's life. How do we do that? Well, we have to take all kinds of measurements. And so that's why the Curiosity rover is going all over Mars, digging and testing. It's looking for trace chemicals that are indicators of water, indicators of any kind of organic activity. And we're also kind of interested in the icy moons of the outer planets. And so we're actually planning a mission out to Europa, which is one of Jupiter's moons, because although it has an icy ocean, it's liquid underneath, and it's possible that there is life in that liquid ocean. So we've got to figure out how do we get to it and how do we determine if there's any life at all. So that determining the existence of life is a huge science problem, multidisciplinary. You can be a biologist, you can be a radiation scientist, you can do all kinds of developing instruments that measure organics. All of these kind of skills are what we need and what we are using to develop these missions that are going to go looking for life. So now I turn to Kepler. And the problem that in the early days they had was that they believed that the solar system, the Earth, was the center of the universe. And so with the advantage of being smart and having discovered how the universe really works, now we know that the sun is at the center. Can you imagine how hard it would have been to think of the sun with the planets orbiting around it? We know that is the motion that is going on here. But if your belief is that the Earth is actually the center, think how hard it would be to explain the rest of the universe. The sun, not too bad, because either we're going around the sun or it's going around us, and the moon, pretty much the same story. But the other planets, come on, they had a big problem explaining the motion, these crazy motions that all the other planets had, because we were at the center when we really weren't. And so that's what really brought this challenge to the protagonist of the movie. And so no spoilers, I'm not going to spoil any of this, but it was sort of struggling with this: is the Earth the center or is the sun the center? And if the Earth is the center, how do we generate these other motions that we're seeing? And so they had all kinds of crazy little circular orbits that the planets were making as they went around the Earth. And those weren't quite right, so they had to add another set of little circles, and it just got more and more complicated. But then there was the proposal that maybe the sun is at the center, which became a whole controversy for other reasons. So it took all of these geniuses to really figure it out. Copernicus started it off. Kepler really is the one who figured out how planets move around the sun and then the math behind it. Galileo made the observations that supported and proved it all. And Newton, what didn't he do? Calculus, physics, light, he explained all of it for us. And it worked up until about the early 1900s, and then we discovered there's this other thing called relativity that it's better just to stay here on Earth and go slow, and then Newton's laws work just fine. But what Kepler figured out, and in particular this third one here, is this relationship between the period of a planet orbiting and its distance from the star. And so it's a complicated math equation, very simple to derive, but I don't think I have time to do it for you tonight, maybe after homework. We use this equation in the mission that I told you about, because when we see one of those planet candidates, we know its period. So we know T. And these are physical constants, 4, pi, g, and the big M. We know those. We can observe the star and know its mass. But we don't know how far the planet candidate is from its star, except we've got Kepler's law here, which traces right back from Hypatia. So that's pretty cool. We're actually using the same knowledge that was generated centuries ago. So my closing note is that, yes, we are using Kepler's knowledge. What does it take to be a scientist? And the most important thing for all of you is just to be really curious. Ask questions, and don't be satisfied until you've got an answer that you stop asking questions. The multi-headed hydra here, these are all questions. More research, because the best thing scientists do is ask more questions. You hardly finish one experiment that answers one question, you get 5 more. So we need lots of smart engineers and scientists to help us answer all these questions. And I want to thank you for your attention. I'll stop here and I'll entertain some questions with whatever time we have left. It's been a lot of fun talking to you, though. So does anyone have a question on anything I've talked about? And please make it easy enough for me to answer.
And remember to go to the microphone.
The Hubble Space Telescope is, I'm sorry, was there another question?
As microphone, I think.
Oh, you want me to stand there?
Yeah.
Okay. Thank you. The Hubble Space Telescope changed everything. One of the things that seems to be standard now is that rather than saying how far away an object is, 5 billion light years, 10 billion light years, we're now talking about how old the universe was when we saw it. So
Right.
we're talking about things that were around 2 billion years after the Big Bang, 600 million years after the Big Bang, which appears to be the limit that I've seen with the Hubble.
Right.
How close to the Big Bang, time-wise, will the James Webb telescope be able to see?
Well, James Webb will not make a significant difference in that particular parameter. We have other missions that are targeted exactly at that question of how far back, quote, in time can we see? And because of the very, very complex dynamics of the Big Bang and inflation and lots of very complicated physical phenomena that were going on in the early creation of the universe, we can probably only get back to about 300 million years before things just aren't going to make sense anymore. I could be completely wrong about that, but we are envisioning a mission right now that would get back farther to about 300 million years after the Big Bang.
Okay. Can I ask one other question?
Okay.
There was recently a crowdsourcing among major telescopes around the planet to photograph a black hole. Are there any other crowdsourcing among Earth's telescopes that are planned in the near future?
Well, that's one of the things we're trying to do more and more now. We're calling it citizen science. It's a little fancier, but it's the same thing, really. The point is for us to get our raw data out as quickly as possible to the public, because there are lots of great minds out there, not only in universities, there's a lot of them in garages working on their own thing. And we want to get that data out there so that people can really use their own creativity to analyze it. So I'd say, in general, that's a direction the agency is going, to publish as quickly as we can and make that available. Good question. Thank you.
Do I have to stand up here?
We'd like you to.
Okay. Yeah. With all the great minds working in NASA and communicating country to country, I'm wondering if there's two things I've really heard about that I'm wondering if any progress is being made, and one is aero sickness that comes from being on jet planes where jet fuel can come into planes. I mean, what good is having all good communications if people get sick from that? There's a lot of information on it online. And the other one is cell phones and that's what mine is. No. Cell phones and cell phone radiation. You talked about not using lead shields or whatever. Are they coming up with anything in NASA that could help protect people on Earth from all the increased amounts of radiation that are being projected out of cell phone towers, things like that?
Okay.
Can NASA help us?
So on the point about the health environment inside aircraft, that is something that the FAA spends a great deal of attention on. They've got the Civil Aviation Medical Institute, I believe it's called, in Oklahoma City, that is looking specifically at the health implications of flying, among other things, pilot health and attention and sleep deprivation and things like that. And so that's something that we have helped the FAA with in the past, but it's not something that we specifically spend a lot of our time on. Radiation is an interesting one because there's radiation everywhere. And right now, all kinds of stuff going through us, we don't even know it, and it doesn't have any effect on us. So there's really, we have to look at the whole picture of radiation, not just one device or one type of transmitter. So we are looking at for the health of our astronauts, though. So I think I'm happy to continue answering questions afterward, but I think we're about out of time now. So we'll call it to a stop here, and I thank you again very much for your attention. It's been a great time.
Questions. We just wanted to finish out the television recording part of this. So if you have another question, go ahead and step up to the mic so everybody can hear you, and we'll carry on.
I have a slightly more organic question. And you were talking about radiation, solar radiation. You also talked about supporting life elsewhere, growing food. So my question is, what is the spectrum in space that is experienced, and what actual types of food can grow? What kind of chloroplast can actually deal with sunlight in space, or is it a modified light that you're actually growing with on these missions?
Okay, the light we get here on the surface of the Earth has been filtered by the atmosphere, and so the most of the solar energy we get is in the visible spectrum, which is no surprise. I mean, our eyes were designed to work with the spectrum that was coming in. So our atmosphere filters out a lot of the UV and a lot of the infrared. Mars, if we want to talk about Mars for a minute, doesn't have much of an atmosphere. And so radiation is a very important concern there. If the radiation would literally just destroy, even if it were warm enough and wet enough, without an atmosphere, the radiation would destroy life as we understand it. We are looking under the surface because things under the surface have been protected from the radiation. But to get back to your question, our sun is putting the same radiation out everywhere, and it's just a matter of what filters you're using to catch the energy. So in deep space around our solar system or on the surface of Mars, it's the same incoming radiation that we're getting, less of it because it's farther away, and it's not getting filtered as it is with our ozone layer and the rest of our atmosphere. And so to successfully cultivate in that environment, we would need to come up with mitigations for the rest of the radiation. Does that answer your question?
Largely. Well,
okay.
Or to put it in more simple terms, can any Earth plant species grow in space, or are you using specially genetically modified or either filtering the wavelengths of light to grow food on these missions?
So potatoes.
Is that an experiment?
We're working on potatoes. And yeah, there are hydroponics on the space station, so we can grow lettuce and things like that. But I think it really does come down to filtering the ultraviolet radiation that would destroy the DNA and kill life. Yeah.
Thanks for being with us. In your excellent history lesson about Kepler, I didn't hear you mention Tycho Brahe.
Well,
for decades.
So Galileo was a student of Brahe's, yes.
Yes,
so that's,
and he used Brahe's data without his permission, because he waited until Brahe died, and then he helped himself do it.
Yes.
So without Brahe, we wouldn't have Kepler.
Thank you. And there are probably a line of another 20 that would line up and say, but I had a part in it too. Brahe had a very prominent role, and it was Kepler never would have gotten to where he did without Brahe's data.
Right.
Yeah.
So my question, a lot of us here are interested in science education. Now we call it STEM for some reason, but really it has to do with how we're going to manage the planet, because we have become, whether we like it or not, the planet managers here because of our sheer power. So I was in 8th grade in '57 when Sputnik went up, And when Homer and the Rocket Boys started their project in West Virginia, where there was nothing else to do. So it was really easy to become interested in rocketry because nobody had cell phones. So what do we do now to help young folks discover the wonders of science and get away from fiddling with their digital devices?
Well, we have to make it exciting, and part of the excitement is making things happen fast. Now, the typical conventional NASA flight program is generally about 25 years in the making. It takes many scientists an entire career to pull off one great mission. We're finding that not a lot of today's generation really wants to look at a career-long investment to get to one fairly singular accomplishment. But we are finding other ways to engage them. And with the advent of drones in aviation, we're able to build and fly things really fast, and we can do things with them that are really fascinating. One of the big challenges, whether we're talking about drones or about spacecraft right now, is what we call swarm management, where you've got dozens of these independent units that need to coordinate to accomplish some mission. And so they're communicating and adapting their mission with each other in order to more effectively do their job. So developing and flying drones is one area that we're getting people really excited about. And on the space side of things, now even spacecraft are getting small. So we have pioneered what we call CubeSats. The basic unit of a CubeSat is 10 centimeters on a side, and we can launch these. One unit, that's a 1U CubeSat, is 10 by 10 by 10, and we can have a 1 unit, 2 units, 3 units. We can stack them up like Lego blocks and build instruments and cameras and sensors and transmitters on them to accomplish lots of cool stuff. And they're so light that most of the time we can get them launched for free, because any rocket that's launching a major payload always has extra mass margin in it. Because you can't launch one that's going to be too heavy, it won't get to space. So they always save some margin until the very last minute. They weigh it and they say, okay, now we need to add another 200 kilograms so that it balances. And typically that 200 kilograms is just ballast. It's just heavy stuff that gets thrown away. So we say, how about we stick a few dozen of these CubeSats in there instead? Off they go. So you get a free ride into space, and you can get up quickly, you can build them quickly, and you can conduct some really cool experiments. And there are businesses now that are built around CubeSats, Skybox, Planet Labs. There's a bunch of them, and they're doing different things. Some of them you can kind of order up photographs of whatever piece of land you own and have them taken from space and get them downloaded to you online, different things like that. So there's a whole industry there. And then the other thing is just the whole commercial space thing with SpaceX and Orbital and all these guys that are now commercial space entrepreneurs. It's getting people excited. So I think there's hope. It's going to be a little different than it was in the old days, though.
We've got, we'll get your question in just a second. We've got a question from our online friends at the Haynes Library up in Haynes. Mm-hmm. And they're asking, where and how is NASA collecting CO2 data associated with permafrost thawing?
So we're, as I mentioned, we're going to be up in Alaska this summer. And I don't have the specifics on it. We're coordinating with the state of Alaska, and we're all going to be flying some drones that have sensors on them, looking at the tundra as it thaws. And so it'll be up north. I can get more details on that. I don't have all the specifics, but that's just one of a bunch. We've worked with the state of Alaska measuring the sea ice, kind of looking at wildlife movements and different things like that too. So all with an aviation type of platform. You've been very patient.
So we were watching a show like a week ago talking about an elevator into the space station. Just like a cable they're trying to create with light and thin and strong and all that. Is that sort of crazy talk, or is that something that you guys are working on? I don't.
That's called a space elevator. And it's something that I think it's been dreamed of for hundreds of years. And there have been a number of very serious looks at what it would take to do that. It's beyond our technical capability right now. It would be really interesting to have that because it would reduce the energy of getting into space by a lot, and the reliability of getting there. But at this point, our understanding is it requires materials that are far, far stronger and lighter than anything we can imagine. Maybe nanotechnology has an answer for us someday in building super light carbon nanotube.
That's what they were talking about.
Yeah, so it's still hotly contested, I would say, that whether it's even technically feasible or not. There are some believers out there, and trust me, if it were feasible, we would love to have one of those. But it's not, I don't think it's going to happen soon. Yeah. Yeah.
Beyond the James Webb Space Telescope, what space telescope are you looking forward to next? Like any plan, like WFIRST or LUVOIR?
Oh, you've got them all. I was going to tell you WFIRST, but you knew that one. WFIRST is the Wide Field Infrared Survey Telescope. That's another one that's going to try and peer farther back into the origins of the universe. Beyond that, we've got another one that was on one of those charts called TESS. And it's a follow-on to Kepler, our planet hunting telescope. TESS, we love our acronyms, Transiting Exoplanet Survey Satellite, I believe. And that one is going to be looking at stars that are basically the closest stars to us. So the Alpha Centauri system is one area that it'll look. There's some other stars in the kind of the 10 light year, 20 light year range. So looking just at stars that are much closer to us, we hope to directly image planets, meaning we actually see them, we don't just see the evidence of them. And if we're really lucky, we're going to come up with some ways to determine if they have an atmosphere and what is that atmosphere constituted of. So that'll be a really exciting one. So there's some other, we're proposing new telescopes all the time. It's just a matter of when does NASA have the budget and the interest in going after a particular one. Let's go over here and then I'll come back to you, okay?
My question is about avoiding bias and searching for life. We're all biased. The only life we know is ours,
Right.
and the organisms that evolved on this planet. Are you trying to broaden your parameters and be prepared for encountering other kinds of life that may not fit your criteria? And surely you're thinking about this, and maybe you can expand on it.
Yes, that's a very valid question, and one that we puzzle over, because if we don't understand that some other form of life, how do we detect it? How do we measure it? How do we prove that it's there? For now, we are sort of accepting the reality that we only understand life as we know it. And by life as we know it, I'm talking basically all the way down to DNA. We're saying we need to see DNA in order to establish the presence of life. And so we're looking at what are the precursors and what are the indicators that there's even genetic material out there. And acknowledging, yes, that is what our missions are focused around, because that's all that we really know how to measure. So at some point, we're going to have to get smarter about how do you define life and how else might it come into existence and evolve. But we don't know how to do that yet, so we're doing the best we can, which is look for what we do understand, and that's the double helix. So if you've got any ideas on that, love to hear you. Yeah.
Question about Venus.
Mm-hmm.
I've seen some proposals of having satellites, even manned satellites around Venus, not going to the surface, because that's extraordinarily hot. It's incredible pressure, atmospheric pressure. But what was it, about 60,000 feet above the surface, you get atmospheric pressure that's approximately what the pressure here on Earth. It's also relatively comfortable temperature-wise. So it would take relatively minimal opportunity to get a spacecraft that orbits the planet and conceivably even have humans living in there. Have there been any steps taken towards that?
Well, Certainly not on the human manned mission to Venus front, but there is growing interest in going back to Venus for the reason you state, that although we pretty quickly determined the surface of Venus is completely inhospitable, the clouds contain organics that could possibly create conditions that were conducive to life. The Russians sent a couple of missions to Venus where they actually flew through the clouds. I don't really know much about what they determined. I think it was mainly the chemistry they were looking at. But there has been some talk even about using an airship that could just kind of hover in the atmosphere for a period of time. And so the way this all works, the way we get our missions and decide what to do, is principally through a government organization called the National Research Council. And every 10 years, they get some of the best minds in the country together and come up with kind of the science agenda for what are the profound questions that we want NASA to answer. And they concern astrophysics, origin of the universe, planetary evolution, and search for life, that kind of thing. And so NASA then looks at missions that support those objectives in what we call the decadal survey. And so Venus is starting to come back up the list. Part of it is driven by the priority from the science community itself.
A different type of question. Where will you be on August 21st, and why?
I know exactly where I'm going to be, and I'm quite fortunate that my father has a vacation home in Central Oregon, and so I just offered to come visit him for a while. So yeah, we're going to go drive off into Eastern Oregon and find a spot. There's a town called Madras, Oregon, that's pretty much right under the path of totality, and apparently it's like Woodstock now. They're just, everybody's trying to get in there. But that path of totality goes all the way across the country. So you just drive somewhere else, and I think there's plenty of room somewhere else. I'm not going to disclose my location, but somewhere in Eastern Oregon. Looking.
Through our NASA at My Library grant, we have some glasses and different things we can send to you. Come by the library and I'll check them out to you.
What are chances the Hyperloop will succeed and will reduce pressure on aviation at the continental scale? Probably not intercontinental for a while, but if that succeeds, we don't need as many airplanes and we don't have the congestion problem. What are the chances it will succeed?
Well, it's got a good financial backer.
Could you explain what it is?
The Hyperloop is a passenger, well, maybe you can describe it better. Don't think of a train, but think of a tunnel with a single occupied vehicle, or maybe, I don't know, a few that's shot through at very high speed of sound driven by, I think, magnetic levitation,
yeah, it's maglev
superconducting.
It's an evacuated tube.
Yeah.
Not a total vacuum, but you reduce the air resistance.
Yeah.
And it's multiple passenger vehicles. 700 miles per hour is their target.
Yeah, yeah. So, I don't know. Many of these high performance transportation systems start out with very low volume and very high cost, and they have to survive as a business long enough to get the economies of scale. And so it's still in the concept phase as far as I know. To think of, there are 40,000 flights, commercial flights per day in the contiguous United States, each carrying around 100 passengers on average. So you can kind of do the math, and I'm just trying to imagine how a Hyperloop would support that kind of volume. But
we heard there was some twittering about privatizing the FAA. How's the NASA funding?
NASA, well, this year's budget was just kind of a carry through from previous years, and so no surprises. But the fiscal 18 budget is really the first one that the new administration gets to define, and that has not passed, of course. It's just a proposal. that was announced in May. For NASA, we're pretty happy with it. So it's going to support almost the entirety of our science program, all of our objectives, a few little nips and tucks here and there, but for the most part, it was a very strong endorsement of what we're doing. There is a little bit of discussion in Washington about privatizing the FAA, but only the part that controls traffic, not the safety and the regulatory part, but the air traffic control part of it. That's a conversation. Other countries around the world do have privatized systems, and they operate fine. So it would not have any real effect on NASA, though, because we simply provide technology to the FAA.
Could you comment on on how much overlap, if there is any overlap, between the Earth observation that you do and the Earth observation that NOAA does? Because I get the feeling that NOAA is very interested in day-to-day and NASA is more long-term, but I'm not sure.
That's kind of right. I think we launch NOAA satellites, by the way. We launch them and get them all checked out and running and then say, here are the keys, have a nice day. So yeah, they're monitoring weather. We collaborate very closely with NOAA, but I think your characterization is correct. We're looking at Earth as a planet, trying to understand the planet. And I think that NOAA is trying to understand kind of the immediate effects of conducting business and life within this environment. Yeah.
Right. So you've worked at NASA for 34 years, you said?
Yes.
So you've seen wide changes in computing styles and processing power. So we hear more and more about quantum computing and how things are going to be changing yet again, and probably rather quickly. So is that something that you're excited to face? How does NASA stay nimble? What do you suggest for the next generation? That's a lot of questions, sorry. But I just want to get a sense that you're kind of facing this new frontier again.
And my center, being right in the middle of Silicon Valley, is kind of the leader for the agency and which way to go with computing. So turn the clock back, when I was doing my PhD research, I was doing something that required a really fast computer. And that's basically what got me to NASA, because at the time, NASA Ames had the fastest supercomputer. It was built by Cray Research, still around. And we had one of the first Cray supercomputers there. And so that was awesome. And I was at Stanford with the other unlucky PhD students who didn't work for NASA, using the crummy computer that Stanford operated, and I was running circles around them. That supercomputer that I was using at the time, I'll go ahead and confess, that was 1984. Doesn't hold a candle to this. So I could have done my whole dissertation on this and still had time to spare. But there's this Moore's Law, does this wonderful thing of making computers faster and cheaper. So now we are still basically using the same architecture of computer that I did, but it's about 100,000 times faster than what I had. We also have the country's largest quantum computer, and it's simply an experiment right now. We really haven't figured out how to use it effectively. It's a very finicky device, and it's not a versatile all-purpose computer. It really solves just one problem right now, the traveling salesman problem, which is if you've got, well, you can think of it that way. It's an optimization problem where if you're the traveling salesman and you got to go to 2 cities, it's easy to figure out the shortest path. What if you have 3 cities? Okay, well, that's not so hard. I can try different permutations. What do you have? 4. Now you've got a whole bunch of different paths you could take. What if you have 100? All of a sudden, the complexity of the problem just explodes. The quantum computer is very, very good at that. It actually is much faster than anything else that we have. But trying to get it to solve a real problem, not just this kind of idealized problem, is where we are right now. And also, it has to be isolated seismically. It doesn't like vibration. It has to be in a Faraday cage, so there's no other radiation coming in, and it needs to be held at a low temperature of 20 millikelvin. So 20 milli, that's like 20 thousandths of a degree above absolute zero. So it's a very special shrine at Ames where we, the computer, please give us an answer kind of thing. So that's why you're not going to have a quantum computer on your watch until we figure out some way to make this all. It has to do with the quantum tunneling and superconductivity that takes place near absolute zero. Until we figure out how to make that happen at room temperature in a dirty, noisy environment, we can't use it really practically. Back here.
NASA is an American enterprise. Are there other organizations around the world doing similar work? And if so, how do you coordinate with them?
Oh, absolutely. There are national space laboratories, I'll call them, all over the world, and we do work with them. And in a lot of ways, NASA is one of our nation's best diplomatic tools because we're really kind of in a altruistic mode with other countries, even our sometimes adversaries like Russia. We work with very harmoniously in space, collaborating and research. The telescope inside a 747 that I talked about earlier, the telescope was actually built by Germany, and they are our partners in that whole program. So they've got their national lab, DLR, that collaborates with NASA. We work with really many countries around the world that have these aligned interests. The International Space Station, of course, was an international effort. Many different countries collaborated and built pieces, Canada and Japan and so forth. So yes, working internationally is a big focus of ours. I think if and when we attempt taking people to Mars, it's going to be an international effort. It won't be an American-only effort. So on the other hand, there are some competitive aspects right now too. The Chinese are very actively trying to get spacecraft to the moon and show what they can do there. So we're interested in collaborating with them, but they're also doing some things independently.
Does NASA do any space camps for kids?
We used to, but sadly not anymore. There was a commercial outfit that actually had got a concession from NASA to run space camps around the country, but they don't operate anymore as far as I know. Maybe one in Huntsville, Alabama. But we do internships, and we love to host students. And I said college students. We actually do host high school students under very restricted conditions because generally they're unpaid positions and there are labor laws that complicate things a lot. But we do have a few high school age students also on center with us. But for the most part, college students and on up, we love to host. And my center hosts right now something like 700 students on site. There's a little over 1,000 people like me there, and then there's 700 of these students, and so it really all of a sudden it seems crowded and can't get lunch at the cafeteria anymore, and all kinds of stuff goes on. But yeah.
Enceladus, a moon of Saturn, Europa, a moon of Jupiter. These and other moons in our solar system are believed to have liquid water under their icy surface. What is the status of various plans to visit and have a robot that would actually become submerged in their oceans?
Yeah, so lots of answers to that. We are in what we call a phase A study of a trip to Europa. It's called the Europa Clipper, and it would be a flyby. When typically, the sequence in any exploration is you do a flyby, then you do an orbiter, and then you do a lander, and then you start doing whatever you want. And about what we can manage right now is a flyby of Europa that would sample its atmosphere looking for organics. Now, Europa is an icy moon, and so it's got, I don't know quite how thick, it's hundreds of meters thick of ice above what we believe is to be a liquid briny ocean. So what business do we have looking at the atmosphere? Well, Europa is in the presence of Jupiter that's so massive that tidal forces on Europa literally wrench the moon around in ways that crack the ice. And when the ice cracks, the liquid underneath comes up and comes to the surface. And on some occasions, it actually is ejected from the surface. And so that's kind of the hope, is that we could send a flyby that would kind of sniff the atmosphere and look for organics. The follow-on to that would be a lander. And a lander would have to have a drill. Now, it doesn't need to drill all the way through the ice. It just needs to drill far enough down to get below the radiation zone, because it's a very high radiation environment. Any life that might have been ejected from the liquid would be immediately killed and destroyed by the radiation on the surface. So we need to get down deep enough to get away from that, which is something like 18 inches or so. Enceladus is an appealing target also, even more appealing in some ways because it has active volcanoes. And so it's literally continually spewing its liquid into its atmosphere. And so we'd have a much better chance of flying through a plume and grabbing something there. That's kind of where we are. Lots and lots of interest. There's, as I said, the Phase A study is being conducted, which basically is a decision gate to say, yeah, it's feasible, and here's what it would cost. And then we just kind of say, okay, Congress, over to you. And if they want to appropriate the money for us to go forward with that mission, we'll do it.
Well, I just want to make a comment. We're at 8:30, so I want to make sure everybody knows that the movie tonight, Agora, is at 9 for free at the Gold Town. And so we'll do maybe just one or two more questions, and then we'll call it a night. And we do have one more question from online from Meredith, kind of a two-part thing here, and it relates to the movie. In terms of the current Earth science NASA fields of research that directly serve the American public, which project are you most intrigued or excited about? And what do you think about the movie Agora's protagonist, Hypatia?
Wait, those are two very different questions. I think I'll answer the second one. I think Hypatia, so I'll say no spoilers again, but Hypatia is, as far as I know, a true historical figure and a very bold female teaching men at a time when that was not done, and in math and science, astronomy and mathematics. And I think it's even more important today to have great role models for people of all walks of life to see that anything is possible and that anyone is capable of learning and contributing in science, technology, engineering, and mathematics. And so I will give Hypatia great props for being a great role model for women. So the Earth science one, we've got so many Earth science missions going on right now. If any one of them can get me back up here to visit you in Alaska, that will be my favorite mission. How's that? Yeah?
Has there any been thought to trying to speed up the data transmission from the Mars rover back to Earth around 30 minutes?
Well, so there's two parts to that. One is just how fast is your computer? And you know, we've got these skinny little network pipes because it all comes back to the weight and the availability of technology and the power it takes to pump data up to an orbiter, which then goes back to our deep space network, which ultimately comes back to Earth. And so those pipes are really skinny because we can't afford too much weight, and that makes us get really clever about data compression and processing on site on Mars before we send final results back. The other part of it is, so every time we launch a new spacecraft, we can do better because the technology has improved. But the other part of it we're never going to get around, and that's the speed of light. And if you say, if you wave your hand on Mars, depending on where Mars and Earth are in their orbits, it's going to take anywhere from 3 minutes to 17 minutes for that signal to get to Earth. Speed of light, that's a speed limit you cannot break, as far as we know. And so we just have to live with that. And that's part of the reason that we want the rovers to be as independent as possible, so that we don't have to have this long delay in communication every time we want to turn left or go forward 5 feet. We want them to figure that out themselves. And that's a big push just for all of us in NASA, is what we now call autonomy. We want those robots, those robotic devices, to make their own decisions and give us back the answers to the questions we want. It's a good question. That?
As a frequent flyer, I guess I know that the enemy is weather a lot of the time. Sometimes getting in and out of an airport, but also sometimes just flying along minding your own business, and all of a sudden it gets bumpy. Seems like that's happening less and less these days. Have you guys been doing work on helping aircraft crews and computers determine the air quality and the ride ahead? And is that something that's
Absolutely, yes. The better forecasting is, we've definitely gotten better at forecasting, and also at flight planning, so that you know where the weather's going. You can develop a flight plan and integrate that with everybody else who's flying, so that you're avoiding the weather. So that's true, and I think that we are doing a better job. There are fewer, have anybody here had to hold before landing at an airport lately? It doesn't happen nearly as much as it used to, because you slow down en route more often now, and you don't even know that. You're just riding along. I'll tell you one little secret, though. Nothing to be alarmed about, but if you've ever been just kind of cruising along on a smooth day, and all of a sudden there's like 2 bumps, they don't even turn the seatbelt sign on, and you just keep on going. Felt like you hit a speed bump. There's a strong possibility that you just flew through somebody else's wake. And the reason that you did it is that our navigation is getting so precise that aircraft are flying very close to the same paths. And so the chance that used to be, our navigation was so inaccurate that we were kind of all over the sky. But now we're getting so good that we're flying over the same piece of air, and we're hitting a wake that you might have missed other times.
Like if you cross behind another aircraft, how far away would you need to be to feel the wake?
You could be, you could be 100 miles away from an aircraft, and the wake persists for a long time. It's just that you never hit it. But it might be that your navigation is so precise that you flew right over that little speed bump. It's not dangerous. It just happens once in a while, and I've heard the FAA guys talking about that happening. So it's completely different than clear air turbulence, where they do turn on the seatbelt sign, and it's bumpy for a while. So, yeah.
I was talking to my science mom, who somehow missed this lecture, unfortunately, but he was it was about 3 in the morning last night, but he was talking about everything is spinning in the universe except the universe. Do you know anything about that theory, or is that true or false? That everything spins, and I don't know if that's true or so.
Well, I think that's a fairly profound question. The universe, it has this fabric of space-time, and so in a sense, we're all moving along the paths that space-time defines for us, and this whole thing about relative motion comes in. Am I spinning, or is the universe spinning, or is nothing at all spinning? Are we just thinking we're spinning because that's the shape of space-time? And how many universes are there? You can read lots of amateur physics, quantum physics books that speculate about all these things. It's fun reading. I understand it for about 5 minutes, and then I was like, I don't know.
Nothing confirmed in all minutes.
No, I think that's far more profound than anything we've been able to figure out so far. Yeah.
One more. Let's do one more.
Yeah.
So your project
project up there, up north in Alaska for doing, like, going to the pilots going through the passes, is there anything with that that would then be able to have that data be given to the National Weather Service so that those forecasts can get better? Because obviously we have an expansive, you know, area to that doesn't have people or
Right. And my friends in the Alaska Department of Transportation like to tell me that the surface of the moon is mapped more accurately than Alaska. We know more about Mars than we do about Alaska. So part of it is mapping, and I've heard some fairly startling stories about how inaccurate the maps are, that literally with very precise navigation now, the mountains aren't where they're supposed to be. Literally, you know, you can plot a route and GPS says something different than what the aviation map says. So that's a big part of the safety equation right there. The reason that the National Weather Service doesn't have the kind of thing that I talked to you there about is that what we came up with is, in relative terms, kind of expensive, because we were using Iridium satellite connections to upload and download the data. Now, for an individual pilot, it's not very expensive. It may be a few dollars on a flight. But for the entire state, 24/7 all year long, there's no budget that supports that kind of data acquisition using the way we did it. We were looking at what can an individual pilot who really cares about his safety and is willing to pay a little bit for it. You got to buy an iPad, and you need to have some Iridium service. Then you can get that.
You know, I just hope the pilots get the PIREP and there's information from them.
Yeah.
And thank goodness for NASA support.
We care deeply about the safety of aviation here, and Alaska does have the biggest general aviation challenge, so it's certainly a good place for us to try and make a difference. All right, I think that was the last question. Thank you.